So we need, as I say, we need invertible for encryption, or invertible or surjective maps for decryption. Okay, objectives you want to do both things. And in this case, the map in the multivariable crypto we'll use is polynomial map. So we have K is a finite field of Q elements. Q is a power of a prime. Okay, this is the finite field of Q elements, FQ. All right, and then we use polynomial. So a polynomial map from P1, PM, M from FQ to N to FQ to N. Okay, but the way, depending, for instance, if we want to use for signatures, you want injective. In particular, you have to also to have impose the condition that N is M is less than or equal than M. If you want something injective, of course, this is a necessary condition, not sufficient, but necessary. And in the contrary, you want for signatures, you want surjective, then we need N. Okay, okay. So that's in principle we have such a map, and how we make how you pretend that, and we need as I say, we need an easy. A map that is easy to invert. F is easy to invert. But more or less, we are using algebraic geometry or any algebraic idea. This is not difficult. How to get maps that are easy to invert. But the difficult part is just, as I say, make up, pretend that it's difficult. How, of course, in this case, the problem, the generic problem is that, of course, that how you invert. You have y is equal to p or is 1 xn, okay? Then the invert is just to solve. Invert is to solve the system given I0, to solve the system of equation P1 of x equal to I1, P of x equal to is0, and that gives you a system of equations. So a system that will be P1 of x minus 1, 0, 1, etc., minus, etc., and you have to solve this system. Okay, you can use, and for a generic, for P generic, this is an NP complete. It's a NP complete problem. Okay, remember that NP complete means essentially that this is exponential. So probably you know the problem n versus p versus NP, polynomial versus non-deterministic polynomial. Okay, this is one of the problems of the century, that if you solve this, they will give you $1 million of dollars. But probably people believe that they are not equal, and if they are not equal, then means that NP complete are exponential. So this implies the NP complete are exponential, is exponential. So if you take a random polynomial, you get something that is exponential to solve. Okay, we are safe. But this, as I explained to you, I mean, I take time to do it. Now, to get a public key crypto system, you need an easy system of polynomials. I said here put P, sorry. and easy, and then pretend who is difficult. So how is this done? So how is this? What you take this map, FQ to the N, we call, okay, I call it P, okay, FQ to the M. This is easy to invert, okay? And then now we take two linear isomorphism. L1, FQN, L1, L2 are linear isomorphisms. Generic means dense. It means dense. Okay, and then this, and then you take the composition. Okay, and then the public key is P bar. That is the composition L1 P L2. Okay, that is this is the one who looks difficult. Okay, and the secret key is of course P L1 L2, because P L1 L2 you can just invert, just inverting L2, inverting P, and inverting. Okay, so this is very easy. The way to pretend that something something easy is difficult, because there will be dense linear map. So even if this has very few monomials, after these two linear isomorphisms, they will get the whole number of monomers. Yes? Ah, sorry. Okay. In fact, this also gives you a hint. So, as I say, this P will be dense, and this also, in fact, gives you the fact that the public key is a dense polynomial, means that this implies that you must use only quadratic polynomial, only quadratic polynomial, quadratic polynomials. So you will see polynomials, okay, for P free bar. So this is the explanation why you can use, of course, qubit will be more difficult to invert, or quartic, but the problem is that the level of security that you need, the cubic and quartic polynomial will get too many monomials. So remember the level of security. For security, the first thing that you need when you have P of x equal to y, okay, this is FQ to the M, okay, you need that, it cannot be, you need to be Q and M, Q to M has to be big, because otherwise you can use brute force, Q to the M has to be big, because otherwise you can just solve the system by brute force. I mean trying to all the possible values. In fact, that's Q to the N. Okay, so that means Q to the N has to be of the order. For instance, now for security we are thinking, as just you saw, something like 2 to the 128. So 128 bits, right? So you need that. Q to the N has to 128 bits. Okay, and then the problem is that usually it's convenient to use a small field. I mean, and that means that then, for instance, you can. I will assume that Q is equal to 2. That's the most use. then you need 128. I mean, if you have for the grid 2, D=2, you need in 128 variables. You can make the computation. Remember the number of monomials. If the number of monomials of degree D in variables n or less than n, in principle has not to be homogeneous, is n plus d over d monomials. And that, for instance, this will give something like 2 to the 10 bytes, something like that. Okay, but if you take d equals 3, then you get 2 to the 15, something like that. And this is one megabyte, but this is 10 gigabytes, and for d equals 4, you have something like 20 bytes. Okay, and then this is already 1 terabyte, something like that. So that shows you that really you need to use quadratic polynomial, or I mean, if you have not many variables, you can maybe use cubic, but mainly you have to use quadratic polynomials. Okay, and in fact, all the systems are like that. Let's say that the only one who is not like that is mine. So I will talk a few words. I will at the end I will explain more how to do the system. Mine is completely to the contrary. My system is just have very few variables. For instance, the number of variables is equal n to the for instance n equal to 8, and then in order to get this security, you need a key q to be something like 2 to the 34, and then you see you get a security of 2 to the 34 for it to 256 bits. Okay, so it's completely contrary, and in fact, and we'll see we use ideas of algebraic geometry. So as we are in a course about application of algebraic geometry, so this is a nice application. Okay, but okay, so I will now give I will explain one or two system of multivariable. We'll start to see how make others the security, how we can attack. Okay, and this part you can find in the book I give to you. All right. So okay, then the first system that was proposed. I mean there were several proposals, but the first that was really interesting was Imai Matsumoto. Or Matsumoto Imai. So, so the first one was Matsumoto Imai. Imai. It's interesting because it gives you use the word-to-word the general scheme that I told to you. This was in the 88, okay, and it's also called MI, or in some place they call it C star. Okay, and then in Imai Matsumoto we have Q is small. Q will be 2 to the A, something like that. Small, less than just 35 or something like that. Okay, really small. And then okay, and then what is the central? And we have to define here a map from FQ, an invertible map from FQ to FQ to the n or to FQ to the n. Okay, and then we have we use the next thing. We consider the field FQ to the n. Okay, so this field of Q, field of Qn element. Okay, remember that this is a vector space is the dimension of vector space over the FQn. over FQ is n. So that means as a vector space, FQn is isomorphic with Qn. In fact, we use an isomorphism, phi that FQn to FQ, Qn, in such a way that x0, xn minus 1, okay, I will use n here, sorry. All right, yes. Is given by x0 plus alpha, x1 alpha plus xn minus 1 alpha n minus 1, okay? Where alpha is a generator of the field. Okay, for instance, we can take FQn plus FQ of x over a polynomial of degree n, irreducible of degree n, and take alpha, the class of x plus multiples of x. Okay, this is a generator. So you have here and then the idea is to use this isomorphism. So the idea, I mean, the design, not the idea, is to use this isomorphism, okay, to get here a map that is easy to invert. Here we have the isomorphism, okay, q to the n. Here we'll have that. There is, okay, fq to the n. Okay, and then this is to invert. Okay, then we in one variable. Okay, this is in one variable, and then here we have n variables. Okay, and then here we use the what I said to you. Here we use two linear maps, two linear isomorphisms. In this case, we have the same fq to the n. L1. Okay, all right. Okay, then how to I mean, what is the how to get an easy invertible map? Remember that in general, in a field of Q an element, we have that for all Z belonging to FQn minus 0. Usually, we'll use to be sort FQn star. We have that this is the group, the multiplicative group is a cyclic group, so of order qm minus 1. So that means that f z qm minus 1 is equal to 1. All right? Okay? And then this gives you gives you the way to get an invertible power. It's the easy way. So because of that you have that z to the a is equal to z to the a prime if a is congruent with a prime mod qm minus 1. Okay? So in particular, then I will take here fz, it will be set to the a. Okay? And then this is invertible if a GCD of a and qn minus 1 is equal to 1. All right? So just, it's like the RSA. This is invertible as far as the exponent is invertible mod qm minus 1 because of that. I think I don't need to make the proof. It's one line, but it's clear, no? I think. Okay? All right? Okay. So now we have many invertible maps. Okay? Many invertible maps that when we pass here, then get something that is more complicated. All right? All right? So, but then we need, remember that I write here, we need quadratic. Okay, we need quadratic, and then how you get quadratic? So you need, in order to get quadratic, I mean, that here you get something quadratic. You need an extra condition.
10 minutes.
10 minutes, okay. So you need an extra condition. Is that, okay, that here, I mean, f bar to be quadratic. Then we turn to the original FQ, okay, in FQ, this extension FQ to the n, all right? And then we can notice in FQ also, we have the same here. You have the same condition. SQ minus 1 is equal to 1, and you want to add the 0, you multiply by SQ is equal to x, okay? And then means the next thing is that when you have the set, this implies that set to any power of q, this is linear in x1 Sn. So the x0, xn minus 1. So if you have this power of 2, when you go down, they will be something linear. It's okay? All right. Okay. Maybe I will try to prove at least one thing in this hour. So the proof is that you should assume that you have set is equal x0 plus s1 alpha plus xn minus 1 alpha n minus 1. Okay. Then you take a power of q. Okay. Then take a power of q. Set to the q will be this to the q to the I. But remember the q is a power of the characteristic. Q is a power of the characteristic. Remember, for power of characteristic, we have always that f plus b is equal times q. This is aq plus bq. Okay, this is what in America they call it the Friesman dream. Because, you know, the binomial is very easy. Okay? So that means here we have to put, you can put inside, all right? You can put here inside, q to the I, q to the I, q to the I, etc. I'm sorry, I didn't write again. So you can put q to the I. And then, because this is our element of the field, okay, we are put a power of here, that means that xi to the q to the ej to q to the I is equal to xj. Of course, this is not true because they are not in the small field, and q can be any power, not n. And then alpha to the q to the I, it has to be I mean any element. So that means it will be a linear combination, a linear Li of x. Alpha Lg of j, alpha j, okay? And you substitute it because it's a general element, so it has this form. And then you substitute here, and then you get, as I say, you get here sum of xj, Lj of x, alpha to the j, something like that, okay? And then it's linear. So, okay, so how we get then, you use a power like that, you get a linear polynomial. So how to get a quadratic polynomial? You take A equal q to A plus q to j. Because, of course, set to the q to the A plus q to j is this set q to A, I times set q to, and then this the power of two, down here it will be the power of two linear forms, there will be a quadratic form, okay? All right? So this is the system. In fact, in my Matsumoto, they take A equal to q to the I plus 1. So you don't need to, and this is the system, okay? And,
Sir, one question please. Sir, under what conditions did you take this A plus B to the power q
yes.
is equal to A to the power q plus B to the power q? What was the condition?
No, I mean, the characteristic of the field is P. So that means that the condition is that Q is a power of P. Okay, that's the only condition. I mean, in a field of characteristic P, we have always that. In a field of characteristic P, we have always A plus B equal to P is A plus B. Okay, so that's, in particular also for the other powers. Okay, it's clear. All right? Okay, so maybe I will, so I'm sorry I was too slow, but I prefer that all the things I talk about become clear. So maybe in the next talk I will explain how to attack the system and what we can do for that, and that's all. Yeah.
Any question from the audience? Okay, if there is no question.